So let's take a look at energy in the magnetic field. The total energy that we'll come up with is denoted by U sub m. Before we look at the magnetic field, let's go back and look at the electric field, and remember that was capital U sub E. Remember that if you're trying to push charge together and accumulate a distribution rho of r, what we're doing is we're moving charges from infinity and looking at the work we have to do that, and so the work that's done is equal to the energy that's stored in the field by doing that. There's a couple of versions of that dependence on the volume integrals. This is the version where you have the density of charge and the self-potential, which is the potential that you're growing as you increase the charge density. And so that's what we mean by the self-potential. So if you take the rho v squared and integrate it over the volume with this factor of 1/2, then you get the total energy it took in order to produce that charge density. You can also express this in terms of electric field, and again it's a volume integral, and so you'd have epsilon 0 over 2 times E squared. Okay, now what is E? E is the field in the volume that's due to the charge distribution that you've created. We can show the simplest case where we have a capacitor that we're charging, and so let's imagine that you have a source of potential that was pushing the charge onto the plates of the capacitor. And so if we're going to put an increment of charge dq, we'll get a change in the energy of the system, or we'll have to do work in order to get that charge onto the plates. And the differential of work is equal to dq times V, and we can write that in terms of the capacitance. This would be C dV, which would be dq times V. If we integrate that, in this case we're integrating over the potential, we get 1/2 C V squared. And this would be the electrical work done in order to charge the capacitor up to a potential V, which is equivalent to a certain amount of charge which we had to put on there to get to that potential. So let's look at the energy. After charging to Q, this work is stored as the electric field energy in the gap. So we're talking about the energy of this region here. If you remember that we can find the E field by just taking the charge density over epsilon 0, where this is the charge on one of the plates per unit area. So if Q is on one of the plates, then if we just divide by area, we'll get sigma. So we can solve this for Q, and it will be epsilon 0 times A times the E field. So that's the charge that's on the plate generating an E field E. Well, we know that the energy that's stored in the capacitor is 1/2 CV squared. Where is it stored? Well, it's stored in the E field between the two plates. So we can play with the various combinations of V, C, and Q, and we can come up with this version here is equal to Q squared over C times 1/2. We know the C of a parallel plate capacitor. That's this equation here. If we simplify that, then our energy that's stored in the E field will be equal to 1/2 times Q squared D over epsilon 0 A. So all I've done is simplified this expression up here. If we now take the U sub E in terms of the E field, so we go back to looking at the E field in terms of the charge, so we're substituting in for Q squared, this expression right here. We're putting that into Q squared, and so we end up with 1/2 times this quantity squared times D over epsilon 0 A. We factor out the A times D. So what we have is this factor here times the volume that's inside the capacitor between the plates. So we have a quantity which we call the energy density times the volume. So here we go again. U sub E is equal to this quantity here, the E field energy density. This is a general equation. The thing to notice is that this is defined at a point. For every point inside the capacitor, this is the value of the density of energy. So to find the total energy, you just integrate over the volume. We can generalize this as a density as a function of position and time. It can be time dependent. The electric field energy contained in the volume tau will just be the integral of the density over the volume. And so this would be the U sub E contained in the volume tau. Well, what about an inductor? So we'll do the same thing with an inductor L and a battery E. So what we're going to do is establish a magnetic field inside the inductor and look at the energy it takes to do that. For right now, let's consider this EMF generating a current that is increasing with time. So that will give us a changing B field. So if you look at the back EMF that's generated by this process, we would have the EMF back fighting the buildup of this field equals L di dt, realizing that I has to be a function of time to make this non-zero. And this opposes the buildup of current. So the source supplying the current, in this case the battery, is doing work against the EMF back at a rate which is given by a power which is equal to I sub t times that back EMF. This is like IV in a circuit. Here's your I right here, and here's your EMF back given in terms of the inductance and the rate of change of the current. Obviously, to raise the current from 0 to this value here requires a total amount of work. And so if we write down that that's going to go into the magnetic field as a function of time, then this would be equal to the power, which is right here, integrated over time, and that will give you the energy. So one more time, this is the power, I sub t times the back EMF right here is the power that we're generating, or the EMF is generating, in order to build up the magnetic field. And so we integrate that over time and we get this expression here where I've changed the integral to I. And forgive me, in terms of the variables here, we could put primes on this time here, and this is then I of t. So we have Li di between 0 and I at the time t. That's a simple integral. We just get 1/2 I squared for the I dependence, and then of course times L. The only reason we left the time in here is just to remind you that as long as the current is changing, we're going to be changing the total energy in the magnetic field. Well, we know how this goes, that if we have basically a limit as to how long we can supply current, at very long times, this will reach a final value, I sub final, and so you finally say, okay, we're done. This is the total energy we've produced in the magnetic field, and that will be 1/2 L I squared final. As long as current flows, this energy is stored in the magnetic field inside the inductor. So realize that if this current were to be turned off, we don't have any field. We have no energy being stored if the field goes to 0. Now that may take time, that depends on the resistance of the circuit, but nevertheless this would go to 0, and so we would have no energy. So to maintain that field, we have to keep supplying current. Where is the energy? It's inside the inductor. Wherever there's magnetic field, that's the place where the energy is stored. The energy, U sub m, is stored in the inductor. It's better to say that it's in the B field inside the inductor. And this is exactly what we showed before, is that we have the energy in the electric field in terms of the capacitance. This is stored in a capacitor, but better said, it's in the E field inside the capacitor, and for parallel plates, it's between the plates. Well, let's take a look at the energy storage in a solenoid. Just like we used a parallel plate capacitor for U sub E, we can use a solenoid to find U sub m. This is going to lead to a more general equation for U sub m. We start with the assumption that we are going to ignore the end effects. This allows us to write down the B inside the solenoid. It's just mu0 n times I solenoid. And don't forget, little n is equal to the total number of turns divided by the length of the solenoid. So for this end effect issue, if you just make L long, you would be able to say the B is basically given by this equation. Okay, the inductance of a solenoid we've already calculated, and it's equal to this expression here, mu 0 n squared times A over L. If we take the B field equation up here and just solve it for I solenoid, then we would have the I solenoid being dependent on B times the length, mu 0 times capital N down here. So if we now write the energy in terms of the inductance, we have 1/2 Li squared. So we put in L, so L is given up here. We put in I, which is given right here, square it, times 1/2. Just substitute it in right here. We simplify that, and we end up with 1/2 A times L B squared over mu 0. So just flip this around so that we have 1/2 B squared over mu 0 times a volume. So we have the quantity here, so I'll just circle it like this, times the volume inside L, and so that's like a density. And so we define then the density of the magnetic field, the energy density, is equal to 1/2 B squared over mu 0. Just stating it in words, this is the energy of the magnetic field. This is a general equation for U sub m, independent of whether or not it's a solenoid or not. Well, just like what we said before for the electric field, the density can be a function of the position and time, and so if we integrate this over the volume, then we're going to get the total energy that's contained in that volume by just doing this volume integral. Once you do the volume integral, you won't have a spatial dependence, but you could be left with a time dependence. This is a more sophisticated derivation of the expressions we just got for the total magnetic energy and the energy density. And where it starts is the differential form of Faraday's law, which is right here. This is one of Maxwell's equations. So if we realize that B can be written in terms of the vector potential, B is equal to the curl of A, we can substitute that in, switch the order of taking the curl and the time derivative so that we end up with this expression here. So if you look, you have a curl of E and a curl of something else, and as I say down here, the curl of something is equal to the curl of something else, so therefore something equals something else. So we set the arguments equal to each other right here. So this is the induced electric field, which is dependent on the rate of change of the vector potential with respect to time. So it's a simpler version of this equation right here. Okay, now we know that in a typical circuit, the power delivered, say from the source, is equal to the current that's produced times the potential of the source. We showed earlier that there's an analogous equation for power that's delivered into a small volume, d tau, and so that's equal to this J dot E. J is the current density and E is the electric field. So this would represent a small amount of power delivered to a small volume, and at that point you have J and E field defined, and the dot product is the power delivered. In this case, the work that's being done is creating B in the volume d tau. Now we go to another Maxwell's equation which relates the curl of B and the current density, and I've solved that for the current density here by just dividing by mu 0. Plugging that into the J dot E induced equation, we would have 1 over mu 0 times the curl of B, so we're putting in J right here, dotted into minus the partial of A with respect to T. So we're going to take this quantity here and integrate over the volume, and that's the volume that should be containing all of the current density, and that will give us the total power that's being dissipated within the volume tau. Sticking this into our rate or power equation, this would be the rate of doing work with respect to time, and so we have 1 over mu 0, and it's basically all of this integrated over the volume. So curl of B and the partial of A with respect to time. So now we'll use this rule that we've used before, the divergence of a cross product. It's equal to this expression here, these two terms. And we're going to take our equation that we have up here, where we have something dotted into the curl, and that's this term right here. So you have a vector dotted into the curl. So you end up with these two terms in such a way that we can put that into the integral. So we're replacing this integrand with this two-term integrand. If you take the first term, it's going to be B dotted into this curl, and then it will be minus the divergence of this vector crossed into the B field. And we're going to integrate all of this over the volume because that's what we're doing up here. I put some stars on here because we're going to need this equation. Okay, so now we're going to simplify, and we're going to simplify the first term here by realizing that we can switch the curl of this, introducing the B field, because if we switch the order of the time derivative and the curl, we'll have the curl of A and then the time derivative of that. But the curl of A is equal to B. So we're taking the time derivative of B with respect to time. And so we're using this expression right here. So we have B dot partial of B with respect to time. We really want something that has B squared in it, so we notice that if we take the time derivative of B dot B, you'll have B dot partial of B with respect to time plus partial of B with respect to time dot B, and realize that those switch. So you can end up with 2B dot partial of B with respect to time. Okay, so now you can write this dot product as 1/2 the partial of B dot B with respect to time. The net result is the first term, this first term up here, is equal to 1/2 mu 0 partial of B dot B with respect to time as the integrand integrated over the volume. Again, we can switch the order of the integration and the derivative. So we have the time derivative of this integral here, so we've just taken the time derivative out. I've changed this to a full derivative because the time dependence is the only thing that we're going to have after we've integrated over the volume. Here's our equation again, the starred one, and we've already got the first term, so now we've got to work on the second term. So here's the second term, and we're going to use the divergence theorem. This is the term we're working on. We've got the divergence of a vector integrated over volume, so that's right here. This is just repeating that. The divergence theorem allows us to relate that to a surface integral, so we have this right here. We take the vector and dot it into the surface vector. This should be a vector. We're integrating now over the surface that covers this volume tau. You can see that we have basically a chance of getting rid of this as we increase the size of the volume. The S bounds the volume tau. If we were to allow tau to expand to all space, this really doesn't change the first term. If you've got everything happening here, so you have J in this region right here, for example. So let's say you take this for your tau. If you take a bigger one, you still contain all of this. A bigger one, you still contain all of this. So therefore, this integral here, the first one, doesn't change. However, the surface requires that you have something that's happening here on the surface. But if you go far away, there's no J, there's no E that is interacting with your surface. And to be more specific, it's J. If there's no J at the surface, then that integrand will go to 0, and so therefore this surface integral disappears. So we're left with the power that's being consumed in order to bring the B field to a value B, and will be equal to the rate of change of this volume integral, and this is over all space. Well, we're back to something or something else. We have the time derivative of something equaling the time derivative of something else, which means something equals something else. What's something? It's this W. What's something else? It's this integrand right here. So we can set then the work done to produce B which is equal to the energy that's contained in the field, is equal to the integral of this quantity right here with respect to time, which is equal to the density of energy, again integrated over all space. So what we have then is our density of energy. This is exactly what we had before, b squared over 2 mu 0. And remember that we can generalize it by letting b be a function of position and time. So therefore our density of energy, magnetic energy, is a function of position and time. And that's going to be given by the b squared over 2 mu 0. To get the total energy, we just simply integrate that. And this, you can see after you integrate, could be a constant if there's no time dependence for b, or it could be a function of time. It is not dependent on position. Just pretend this is the total volume, and here's where everything is. It represents the total energy that's contained in that volume. In this case here it's all space, so it's all of the energy that's contained there. Well, let's take an example of the coax. So we have this coaxial cable, and it has the inner conductor of radius A and the outer conductor of radius B. We have currents flowing in opposite directions on those conductors. So inside it's going this way, outside it's going this way. What we'd like to do is determine the energy of the magnetic field which is created by these currents per unit length of the coax. So let's let L be the length of a part of the coax, so we'll just take this L to define a volume. If we take circles that are perpendicular to this conductor here, and I'm not drawing this very well, but it's a circle concentric to the symmetry axis. If this is Z, for example, it would be perpendicular and centered along the Z-axis and taking advantage of the cylindrical symmetry. The radius of this circle, S, is going to be between A and B, so we're in the space between those conductors. So if we use Ampere's law for this volume, we would take the integral of this B dot ds along this path that's the circle around the conductor. So if we take B dot ds, integrate it around that path, this will give us mu 0 I enclosed. This will allow us to get B. Well, we've done this 100 times. This is the B field due to the current in a wire, and so when we're finished we have this dependence on the radius of the circle, which is the S dependence of the B field, and the direction of the B field will be phi hat. We assume that in both conductors that B equals 0. We could add corrections for this, but right now we'll just assume it's 0. Outside both conductors, if we're out here, the I enclosed is 0, so therefore B outside is equal to 0. So to find the energy per length, we find the energy density and integrate over the volume, and then when we're done we'll just divide by L. We could either use the inductance equation that we had before, or we can use the density function. This is the energy density of the magnetic field, and this is the total energy per unit length given in terms of the inductance L. Here's our B, and so let's use L to find the energy. The first thing you do in order to get L is find the flux, and the surface that you use is one which has to subtend the flux once. If you, for example, use this surface and then drew another one here, like that, use this one and this one, you'd get 0. You need to restrict the surface to one side of this region here. So we call that the surface S for the flux. Well, if you take advantage of all the symmetry, this will just be the scalar B sub S, and ds will be equal to the length of this surface S times the differential ds. So what I'm doing here then is, here's the length of the surface, and then we're taking a little ds along the S direction, and that'll give us the area of this strip here. Then we integrate over little s between the inner and outer conductors. So we're integrating from here to here in terms of S. Put putting in our B of S for the field due to a wire, which is what we have here, you can collect the constants, which is right here, and then you're left with the 1 over S integral, A to B, which gives you the natural log of B over A. So that gives you the inductance then by just taking the flux and dividing by the current. And that's what we have here. We've done this before. So this is the inductance. The inductance per unit length is to take L and divide by little l. And so that's what we have here. So going back to our total energy then, you remember the total energy is 1/2 Li squared. To get this per unit length, we divide by L. And so when you're finished then, you have this quantity here as the total energy that's contained in the magnetic field between the two conductors per unit length, because we've divided by the length of this segment here. Okay, so now let's use the energy density, and for that we're just simply going to use B squared over 2 mu 0. We have B up here, so we can write it in terms of the current and the parameter S. Realize that this is a density and it depends on S. This is the only parameter it depends on. Okay, so we take this energy density and put it into a volume integral. This only depends on S, but it's still a volume integral. So we have to write a volume element. And so that's what I've done here. It's going to be 2 pi s times L times ds. The 2 pi s, so let me just draw a circle. This is the circle that we're forming this volume. Here's our s, like this. And then we have another circle, which is at s plus ds. So we're really talking about this volume. That's going to be a area and then times L. That will give us the volume element that we wish. So here's the circumference times ds, that's the area, times L is the volume. So we put in U sub m, this is U sub m up here, and that has an S dependence also. So 1 over 2 mu B squared times the volume element. Collect all the constants, so we have out here all the constants, and then we're left with the familiar integral of ds over S from A to B. That gives us the entire volume contained between these surfaces if we take into this account the length. So here's the total U sub m in the entire volume of length L. And so if we divide by L, that will give us the total energy divided per unit length. Lo and behold, we get exactly the same answer that we got using the inductance. So next time we're going to take a look at Maxwell's equations in more detail and the concept of displacement current.